I'll double check. For now, though, let's just look through these problems. The whole purpose of 4.0 is just to verify that you know how to factor and then how to simplify. So for instance, in number 1, and again, we're just going to do these quickly, so write down what I write down and ask me any questions. Number 1, we have y squared plus 2y, and then y squared minus 4. All of these are rational expressions. They're all rational functions. And the idea is that you are now understanding orders that anytime you see a fraction, like 3/6, you should simplify it. And anytime you see a square root that's simplifiable, you should simplify it. So like that. And anytime you have something that is factorable, you would factor it. That's just kind of like an assumption, is that these things are just things that happen automatically. You're walking down the street, you see any one of these 3 things, you would start to shake until you go over and simplify it, and then you'd feel better again. Right? So in this case, what can we factor out? We can take a y out of the top, and then on the bottom, we can do difference of squares, y plus 2, y minus 2, and then we can cancel out those y plus 2 terms, and you end up with y over y plus 2. Now we know a lot now about rational expressions because now we can say to ourselves, hey, that's a whole. And we can say, hey, that's my vertical asymptote. And so again, this whole section 4.0 is just to verify your factoring skills. So like for instance, in number 2 here, it says x squared minus 11x plus 24, and then x squared plus 2x minus 15. We just want to see you factor it. So like up top, what multiplies to make 24 that has to make 11? Now, you can sit there and go through it all in your head, or just make a factor tree, factor table. So 24 is 1 and 24, 2 and 12, 3 and 8, 4 and 6. So which one adds to 11? 3 and 8. So that would be x minus 3, x minus 8. Then on the bottom, again, if you want to make a factor tree, that's very helpful factor to people. So what multiplies to make 15 adds to make 2? Yeah, you got it. X plus 5, x minus 3. And it's not at all surprising to see that they would give us a problem where 2 of the factors cancel. Well, you know, 1 on top, 1 on bottom. So again, that would be the location of the whole at x equals 3. And then the leftover bit, really the leftover bit is where you can really now see your x-intercept is the numerator and your vertical asymptote is this. Because we wouldn't want to accidentally look at this x minus 3 and say that's an x-intercept. Because there's actually a hole at x minus 3. There is no x-intercept there. Okay, so that would be my answer there. Now, in a problem like number 3, that's checking to make sure that you remember how to factor something where the first term has a number on the x squared. And that just takes a little bit more work. You need some scratch paper, and you have to sit there and do that long problem where you rewrite the middle term. So I'll just do one of them. Let's say we did 2x squared plus 3x minus 9. How do you start the problem? The 2 is a problem, and it's part of the solution. What is it? What are you doing?
I'll just define multiple.
2 times 9?
1.
Good.
No, I'm already doing this. I think I'm ahead of you.
Oh, are you doing rational roots there, or are you trying to factor this thing? Oh, okay. And you probably just have your own method for doing it, where you think, okay, 1 multiplies by 2, etc. Well, the way that we covered in class was to multiply 2 times 9, which is negative 18, and then do the factor table. 1 and 18, 2 and 9, 3 and 6, and then say which one's add to make 3. So that would be the 3 and the 6, because one of them will be plus, one of them will be minus, because if you multiply to make a negative, that's plus times minus. So that means we have a plus 6 and a minus 3. So what we do is you rewrite the middle term. This is the method that we discussed in class. That's minus 3x plus 6x minus 9. And then you can factor by group. So wait, don't worry, that's not the technique you were doing? Okay, but if you still get to the same final answer, that's okay. Because I know that you could always do other methods, but this is like the legit method from the book. So here we can factor out an x, 2x minus 3. And here we can factor out a 3. So that's also 2x minus 3. And since the 2x minus 3 is the same, that means we are successful in factoring. And the x plus 3, the leftover bits out front, become the other factor. So that was all just the work to factor the numerator. So that's 2x minus 3, x plus 3. And then the one on the bottom, we'll go ahead and say is 2x, is it minus 3 and x minus 1? Yeah, that's it. Okay, so that's how it factors. And again, I skipped over the work to factor the denominator, but that is the whole point of the problem, is to factor. Because then the 2x minus 3's cancel out, and that means that there was a whole at x equals 3 halves. Does everyone see where I got the answer 3 halves? Because you said 2x minus 3 equal to 0 and then solve for x. So 2x minus 3 equals 0 is the same as 2x equals 3, which is x equals 3 halves. So there's our whole. And then the other one is our vertical asymptote, and the top one is our x-intercept. How does everybody feel about this so far? 4.0 really is just like a warm-up to just factor everything. But we already know about x-intercepts, vertical asymptotes, and such, so we're labeling that information as well.
So you want to factor, or we have these type of problems, and then factor in the y-intercept?
Right. X-intercept and the vertical asymptotes and all that. Yes. Yeah, essentially you'd be given a problem, some rational function, and then your expectation is to describe it completely. Okay, so that was 1 through 3. This is a good warm-up. Look at number 4. It's a little different. Why does 4 feel different? Yeah, there's a multiplication of 2 fractions, first of all. And it's just a bunch of variables. And there are no factors, per se, where x minus a number. And instead, we just look for whatever opportunities we have to cancel things. So for instance, I know I can cancel out my x. And I know that 7 goes into 14 twice. And this is called cross-simplifying. So I'm allowed to cross-cancel things from one numerator with the other denominator. And we're left with 2y times 3 is 6y over d. So that's just a reminder of the technique called cross-simplification. Now, we'll just do 1 of 5 or 6. We'll just do 5. A problem like number 5 is just lots and lots of factoring and then lots and lots of canceling. So as soon as I'm done writing this down, I'll just immediately turn around, factor everything, like you do. As you're walking down the street, you see a factorable expression, factor it. So on the left, I would have, what, x plus 9, x minus 5? You all agree?
Yeah.
Multiply to make 45, adds to make 4. Now on the bottom, I would have x plus 9, x plus 3. 12 multiplies to make 27, adds to make 12. Then on the right, we'll have x plus 3, x minus 3. And down below, we have x plus 5, x minus 5. Now, I'm going to show you a really subtle point here. That is a subtle point. You see, it's a subtle point. It's a point. It's very subtle. Now watch what I'm about to do here. I have 2 fractions being multiplied with a multiplication dot, or watch how I transform it. It's one big fraction. Is there any difference? It means the exact same thing. So whether you just write it as one big fraction, or you leave it as 2 separate fractions as a dot, the point is you have one big numerator and one big denominator. And now we can go through, we can cancel the plus 3, we can cancel the minus 5. Anything else? Oh, the 9s. And we're left with this x minus 3 over x plus 5. So that's interesting because the problem started out with apparently 4 x-intercepts and apparently 4 vertical asymptotes. But the fact is that 3 of them all eliminated as wholes. So that's a hole, that's a hole, that's a hole. And we actually only have 1 vertical asymptote. And we only have 1 x-intercept. So there's just a lot of extra information in there that has no impact on the graph except to produce holes. Speaking of holes, we didn't talk about this before, and this isn't a joke, but do you know how to make any graph holy? Church? Yeah, take it to church. Exactly right. Let's take the most easy graph you can imagine, which is a straight line, 2x plus 3. All right, so here's just a line. Are there any holes in a line? No, of course not. So how do you make any graph wholly? What you do is you start contributing the same factor to the top as you do to the bottom. Now, first of all, did the graph change? It's still my line. However, do I now have a hole at 2? I do. So I just made my graph wholly by contributing the same term to the top and bottom. So for instance, let's say I want to put in a hole at x equals -10. I can just contribute the same term, x plus 10 and x minus 10. Oh, no, x plus 10, sorry. There. Same line, only now I have a hole at -10. Boy, it's tough to, there we go. So that's how you make any graph wholly. Now, you know, it'd be really weird. What if I, on top and bottom, put every number imaginable? Like, what if I put up at the top there, x minus 0.1, x minus 0.2, x minus 0.3, and I did all infinitely many numbers in the top and all infinitely numbers on the bottom? I would have just put infinitely many holes into my line. And then what would happen to the line if there were infinitely many holes in it?
There'd be no line.
You know, it just disappeared, right? So you could theoretically, point by point by point, delete the entire line. Okay, so there was number 5. Let's skip over number 6 and take a look at division. Bonus joke. Why do math students wear glasses in class? It helps with division. Okay. So let's take a look at number 7. And number, oh, no, not number 7. Let's skip number 7 because it has all that painful factor. Let's do number 8. I know, number 7 was a nice problem, but let's do number 8. So we're about to factor all those things. So I'm going to write it down right now, already factored. So that would be, gosh, what multiplies to make 9? 9 and 10. So x plus 10, x minus 9. And then 1 multiplies to make 60. 6 times 10, x plus 10, x plus 6. And then we're dividing by x plus 9, x minus 9. And then we're doing x plus 6, x minus 6. Yes?
When we get to a problem that so you can't factor, is it safe to assume that one, like the top one you factored, is going to have a term that's similar to the one at the bottom, or the same to the one at the bottom, which is when you're going to be canceling out?
It will often happen that you'll cancel out a factor and it'll be a whole. But sometimes you don't cancel anything. Yeah. Okay, so folks, what do we do with the division line now? Am I allowed to just go ahead and continue that line again and make it one big fraction? Yeah, we have to multiply by the reciprocal. So the fact that it's divided by this fraction, I really now just create a new fraction where I keep everything on the left the way it was. But now I bring this denominator up to the numerator. And then I bring that numerator down to the denominator. And then that, once again, results in lots and lots and lots and lots and lots and lots of cancellations. Yes, the division is the same as multiplying by the reciprocal. There, let me look at that. All right, so that's one thing you can do with rational expressions. You can factor, you can multiply, you divide. The next thing you can do is a little bit more complex, but not much. Number 9 is just barely more work. And number 9, what are we wanting to do? We're wanting to subtract 2 fractions. Now let's just remember, how do you subtract 2 fractions normally? If I have 1/2 minus 1/3, what do you have to do? You find a common denominator. Now, you all know numbers, and so you can look at 2 and 3 and say, what's the smallest number that 2 and 3 both go into? And you'd say 6. And you'd say, okay, over here I'm going to multiply top and bottom by 3, and over here I'm going to multiply top and bottom by 2, because that way I have a 6 in the denominator, and then that's 3 6 minus 2 6, and then you can actually subtract. When you have the same denominator, you keep the denominator and you subtract the numerator, so 3 minus 2 is 1. In this case, we're dealing with variables, so it's not like you just say in your head, what's the least common denominator, or the lowest, what's the common denominator for x plus 2 and x plus 3? There's no number that comes to mind, like when you think 2 and 3, you thought of 6. But it works the same way, that each denominator wants to have the same number down there. Hector?
One of the problems with given somebody that you gave to assignment, what I did is I just multiplied them by each other.
Yes, you can absolutely do that. In fact, you can always do that. So like for instance, this denominator has an x plus 2. This denominator does not have an x plus 2. So I will give this denominator and numerator an x plus 2. And then this denominator does not have an x plus 3. So I will come over here and give it an x plus 3 on the top. Now, you notice that all I did was multiply top and bottom by the same number. I did that here. I multiplied top and bottom by 3, and here I multiplied top and bottom by 2. The only difference is I'm multiplying top and bottom by by an algebraic expression, a factor. Why are we allowed to multiply top and bottom by the same number? You have to. Why? Makes it even as opposed to odd?
No, like I was looking at it as quantity over size.
Uh-huh.
So you have size 2 minus subtracted by size 3.
Uh-huh.
I think it was something.
Good. I don't understand size. You mean size 2 minus size 3?
Yeah.
Oh, you mean like a piece of size 2. A piece
Right.
Of
So you have a quantity, right? And underneath you have a size. So you have one piece of this thing that makes it
right.
a whole. So
Okay, I see what you're saying. So,
that's what I mean by making it even. The way I look at it
you
is
meant
way
to say,
different.
yeah. Okay, so folks, but what is 3 over 3? 1. And same thing, what's 2 over 2? 1. That's why you're allowed to do it, because when I multiply 1/2 times 3 over 3, I actually just multiplied it times 1. And if you multiply times 1, it doesn't change the value. So multiplying by 3 over 3 is valid because I didn't change the value of 1/2. And here, if I multiply times x plus 3 over x plus 3, what is x plus 3 over x plus 3? Still 1. So I'm allowed to do it. I'm allowed to do it because I didn't actually change either value. So now what do we have? On top, I have x plus 3 over x plus 2, x plus 3. And then I'm going to subtract x plus 2 all over x plus 3, x plus 2. Now you notice I didn't bother writing in x plus 3, x plus 2. We know what those are. Okay, so now that they're the same denominator, what can we do? Now we can just subtract the numerators. So we have x plus 3 minus x plus 2. And you'll notice I kept the parentheses on x plus 2 because I'm about to subtract. What does that mean I have to do? You have to very carefully distribute that minus. So what I really have now is x plus 3 minus x minus 2. Which gives us, the x's cancel out. And so it's 1 over x plus 3 plus 2. You'll notice I finally put the denominator in at the end.
In this equation, distributing the negative is optional. Because I just did just subtracted x minus x and then 3 minus 2.
Well, you just distributed the minus.
I guess I did.
Yeah. Yeah. Equivalent. Yeah, you did the same thing. All right, so there we go, folks. We just simplified. We had a fraction minus a fraction, and now it's simply equal to a fraction. And you'll notice that if I let x equal 0, then this becomes 1 over 2 and 1 over 3. And I know what 1 over 2 minus 1 over 3 is. It's 1/6. And if I let x equal 0, that's 3 times 2, which is 6. So you can check your answer by plugging in an easy number for x. Okay, so that's one way to deal with subtraction of rational expressions. Let's try number 10. Does anyone else think this room is warm?
Yeah.
It's a little warm. Doesn't help that I'm up here working out. All right. So number 10, we would like to subtract those two expressions. And you'll notice they do not have a common denominator. But we will immediately factor them. So let's see here. The first one factors into x plus 2, x plus 1. And the second one factors into x minus 5, x plus 2. So we look at those denominators and we say, what do they both have? They both have the x plus 2. The only difference is this one has an x plus 1 and this one doesn't. And this one has an x minus 5 and this one doesn't. So we're going to contribute the terms that they each need so that they will become the same. So for instance, this denominator needs an x minus 5. I'll contribute to the top and the bottom. And this denominator needs an x plus 1, so I'll contribute to the top and the bottom. And now they have the same denominator. Once they have the same denominator, you can go ahead and subtract the numerators, so that's x minus 5 minus x plus 1. And then again, we distribute that minus sign, and the answer would become x minus 5 minus x minus 1. And that becomes, the x's cancel out. It's negative 6 over that. What's that, Emily?
If Matthew can you tell us
The selfish child theory?
Yeah.
Selfish child theory. And that's the other way you can think about this, is that if each denominator represents a little selfish child who's like 2 or 3 years old, and they each look at each other's denominator and say, you know, this child would be like, you have an x minus 5, I want an x minus 5, and then pop stomp their feet. And then this denominator would say, you have an x plus 1, I want an x plus 1, and then they would be dead. And so by my selfish child theory, each denominator wants the same toys. I treat each factor as a toy. And that's just how I think about it in my head.
It's called tantrum.
Yeah, you call it tantrum theory. Okay, now notice what was really interesting here. This expression had 2 vertical asymptotes. This expression had 2 vertical asymptotes. The final answer has 3 vertical asymptotes. And that kind of makes sense, because you're combining a graph with 2 vertical asymptotes with another graph with 2 vertical asymptotes, and one of the vertical asymptotes is the same, so you end up with 3 vertical asymptotes. We'll do number 11. Then we're going to skip over number 12. Let's see. All right. Then number 11. We have 9 over x plus 7. And I would recommend go ahead and put any binomial in parentheses. And then on the second way, we have x plus 133 over, and I would go ahead and factor that. X squared minus 49 is a difference of squares, so x plus 7, x minus 7. And so by the selfish child theory, this first fraction wants an x minus 7 in its denominator as well. So x minus 7. Of course, it's not fair to call it a selfish child theory, because I know adults who get it the same way. Maybe it's just a selfish human theory. All right, so now that we do have the same denominator, we can add the numerators. So that'd be 9x minus 7 plus x plus 33, 133. And then we distribute the 9. So 9x minus 63 plus 1x plus 133, all over the same denominator. And then our final answer is 10x plus 70, all over x plus 7, x minus 7. Are we done?
No.
What else can we do?
Yeah.
You can factor 10 out of the top. Now, again, factoring is a standing order. I got rid of my standing order list. If you see a fraction, a root, or a quadratic, you have to factor whenever possible. So here I factor 10, and that takes, I leave behind x plus 7, and then I have an x plus 7 at the bottom. And our final answer is just 10 over x minus 7, which is a very simple expression. That's just a rational function with 1 vertical asymptote at 7. Of course, there is a hole. We took away the hole at negative 7. Notice this one's crazy. Okay, it's just weird to think about. If you don't think this is weird, that's fine. You can ignore this. But notice when we looked at 9 over x plus 7, that is a graph with a vertical asymptote at negative 7. And then if you look at the graph, so I'm going to turn that off. Then if you look at the graph, x plus 133 divided by x squared minus 49. Then that's a graph with 2 vertical asymptotes, 1 at 7 and 1 at negative 7. And yet, when I add them together, now, okay, so again, here was the first one. vertical asymptote at -7. And then here's the second one, vertical asymptote also at -7. But if you graph them both simultaneously and then you add them together, okay, so I'm going to add this one to it, the vertical asymptote on the left disappears. And it simply becomes a hole. Wait, where's -7? Oh. My goodness. It won't even let me look at it. It won't even let me look. Desmos has been very weird today. In the previous class, I couldn't get it to show a lot of holes.
Is there another way to maybe where those two lines are at?
Oh, what? That?
No.
Where?
Uh,
Oh, that
yeah,
thing?
like right there, is there a way we can plug in our equation using that answer?
I don't know. I mean, I suppose I could always just graph the vertical line at -7 and see if it gives an intersection point. And you'll notice it doesn't. It's not giving me the intersection point because there is no intersection point. But still, that's very strange. Desmos has never behaved like this before. You can see it's literally skipping right over. It's just going dark. That's kind of scary.
It's a bucket system.
A bucket system?
There's a bug in the system.
There is a bug in the system. I feel like whatever they did over the weekend must have affected it. Because no matter how much I zoom in, it's still not showing me the hole. It's just skipping. Look at it. It goes blank. That is so creepy, scary. Oh, all right. All right. Folks, I think we're good with these. So let's move on. Although I suppose there was another type of problem. Should we at least look at it? How do you solve a problem like this? Or, well, they're both the same. So let's look at this one. Number 13, what would we do? What would we do?
Could we multiply the top by P4? P positive, P get positive one?
Multiply by what? Well, let's look. In both the numerator and the denominator, we want to add two things together. And what do you need anytime you add fractions? Yeah, it needs to be a fraction, first of all, and you need a common denominator. So on the top, I can go ahead and make a common denominator by multiplying by p. And then on the bottom, I can make a common denominator by multiplying by p squared. And now I have a whole new problem. So on the top, I have a common denominator of p, so I can write p plus 4. And on the bottom, I have a common denominator, so I can write p squared. And on top is p squared minus 16. Now that's just step one. Now there's a lot of different ways you can solve this problem. This is not the only way to solve this problem. Maybe you're thinking of another way to solve this problem. But now that I have this, what I have is this fraction divided by this fraction. And if I were to write that out, of p plus 4 over p divided by p squared minus 16 over p squared, then how do you rewrite division again? Division by a fraction is multiplication by the reciprocal. So now I can write this, multiply by p squared over p squared minus 16, which by the way is p plus 4, p minus 4. So now I can cancel out my p plus 4s. I have a p on top and bottom that I can cancel out. And I'm just left with p over p minus 4. Any questions about that one? All right, so 4.0 was all about seeing how your factoring skills play into the simplification of rational expressions. Now that we've seen 4.0, we've already done many problems from 4.1. Well, okay, 2 problems. We did 2 problems. So let's go in and do a couple more problems of graphing here, and then we'll move on. So is everybody looking at 4.1? And did we already do number 1 and 2? So we're on number 3? Okay, great. So we're going to go through the whole A, B, C, D, E, answer all their questions, and let's see. Those are the questions. Will you all remind me what the questions are as we go? The first one is domain. So how do we find the domain? Here, I'm going to write down part A. So A, domain. And our function is x over, now should we go ahead and factor that? Might as well. So that'd be a 4 and a 3. X plus 4, x minus 3. What multiplies to make negative 12, that adds to make 1. Okay, so what is our domain? Any number in the universe except for those numbers that cause you to divide by 0. So the domain would be x can't equal negative 4 and 3. Now part B is what? The vertical asymptote. So which one is the vertical asymptote? Because keep in mind, here I'm going to draw this domain. Your domain information is in the denominator because you're not allowed to divide by 0. So this is my domain exclusions. And either one of them is a vertical asymptote, the other one is a hole, or they're both holes, or they're both vertical asymptotes. Yeah, they're both vertical asymptotes. So I'm going to go to my VA underneath both of them. And so in part B, the vertical asymptotes are the vertical lines, x equals negative 4 and x equals 3. Notice how weird this looks. Okay, does someone not in the context of this class, if they literally watched us say x isn't equal to negative 4 or 3, and then in the very next line we said x is equal to negative 4 and 3, they would think we're crazy. Like, which is it? What are we saying? But notice that we're saying 2 different things here. First, we're saying you can't actually plug negative 4 and 3 into the formula, because then it'd be undefined. The second thing we're saying is that these are equations of lines. That's the vertical line. This is a vertical line. So in this context, we're calling that an x value that you're plugging into the function. In this context, these are equations of vertical lines. So it's very different context. Okay, part C. Emily, what was part C? Are there any? Okay, holes. So are there any holes, folks? No. No holes. Part D. Any what was part D? Horizontal asymptote. Okay, so the horizontal asymptote, you do the ratio of leading terms. So in this case, our ratio of leading terms is the x over the x squared, which simplifies to just 1 over x. And the essential rule said that if you take the ratio of leading terms and the power on bottom is bigger than the power on top, then the horizontal asymptote is simply the x-axis itself, which is the equation y equals 0. So in this case, our horizontal asymptote is the x-axis itself. You actually don't even need to simplify it. As soon as you see that the numerator has a smaller exponent than the denominator, you just automatically know that the horizontal asymptote is y equals 0. Okay, then what's part E? Omar, what was part E?
E is minus that.
Oh, and there is no sine asymptote because it's one or the other. It's either a horizontal asymptote or a sine asymptote. And then part F says to graph it. Okay. So what other information do we need? We need the y-intercept, which is f of 0. So plug 0 in. If I plug 0 in into the original, if I plug in 0, I get 0 over negative 12. And what's 0 divided by negative 12? It is 0. And then x-intercepts, the x-intercept is anywhere the numerator equals 0. And the numerator will equal 0 when will the numerator equal 0? If x is 0. So our x-intercept is also 0. So now we have all this information, and we can go graph it. So we now make a graph, and we say that we have a vertical asymptote at negative 1, 2, 3, 4. So there's one vertical asymptote. Another vertical asymptote at 3, 1, 2, 3. A horizontal asymptote y equals 0, which is the x-axis, the x-axis itself. And there were no holes. The y-intercept was 0, the x-intercept was 0, so we just have 1 point. Now, taking a look at this, not many people would just be able to look at that and then say, oh yeah, That's what your graph looks like. I mean, you have very, very little information. You know that your graph has to cross through that point, and you know that you're going to have some swoopies. But where will the swoopy go, and what's going on in the middle? So at this point, you can either make a table of values. So let me say what that would look like. If you wanted to sit there and make a table of values, you would have to, say to yourself, where would I like to see some dots? And I'd like to see a dot in here somewhere. So maybe I'll make a table of value for the number -2. And I'd like to see a dot over here somewhere, so I'll plug in 1. I'd like to see some dots over here, so that would be maybe 4 or 5. And I'd like to see some dots over here, maybe a -5 or -6. And that would be a responsible number of tables of values, or a responsible number of x values to plug into a table. And once you plug all those numbers into your table, you get a bunch of outputs, which is a bunch of coordinates, and you'll put all those dots up there, and then you'll know what your graph looks like. So for instance, I'm just guessing here, I should end up with a swoopy there, and then a swoopy here, and then a swoopy
The other way.
What's the other way? Thank you. Yeah, see, I'm just guessing right now. Should I be guessing? No, I should just graph it. And or make the table of values. So I'm going to go look at my graph, which is,
Everything else is good though.
oh, thanks, x squared is x minus 12. All right, there we go. Okay, so that's what our graph looks like. And the table of values would have bore that out. Had I actually found some dots, it would have, done something like that. And then that would have given you the indication of what the rest of your graph should be.
Another way to find that is to see if your numerator is a positive or negative as well.
Right, you mean strictly if the numerator is positive or negative?
Kind of, yeah.
It almost works perfectly. Over here, if your x value is positive, the whole graph is positive. And over here, if your input is negative, then it's negative. But in the middle here, it's switched. And a positive number becomes negative, and a negative number becomes positive. But you're right, you could do a sign analysis. Yeah. All right. Well, there's that one. So which other one should we try? We don't have to do all of them. How about we do number 5? I would like to do number 5. You can just cross out 4. Let's do 5. What?
And then for the fun.
Oh, it did it?
To me, it did.
Oh, well, let's look at it, folks. Here. No, well, I mean, let's just look at it. Like x cubed plus 1, and then divide by x squared minus 1. Is that it?
Yeah.
Yeah, that is interesting. Oh, and actually, silly me, we are going to do it. We absolutely are, because what do you notice about this one? What kind of asymptotes does it have? It has a vertical asymptote, which you can see the vertical asymptote is at 1. And it has a slant asymptote. And that slant asymptote is, I think, at x plus, no. Is that, yeah, that line right there. So first of all, folks, appreciate the slant asymptote. This purple graph is coming down, it curves up, and then it gets closer and closer and closer to the red line. So it is indeed a slant asymptote. The asymptote is slanted. Same thing down here. The purple line comes up, and then comes down, and it gets closer and closer to the red line. Never to touch.
If I remember correctly, your slant is actually the long division.
Yes, that is correct, and that's why we definitely want to do this one. So we can all thank Lee for reminding us how important this problem is. So let's take a look at number 4, and that's probably the number one thing we want to look at is how do you find a slant asymptote? So first of all, looking at this problem, just thinking about slant asymptote now. The ratio of the leading terms is x cubed over x squared. And that ratio itself simplifies out to x over 1, which is the graph, or the straight line, I should say, mx plus b. That is mx plus b. And if you'll recall, that was the actual slant asymptote. So sometimes the ratio of leading terms actually does give you the slant asymptote. That was our slant asymptote, 1x plus 1. I'm sorry, 1x plus 0. So that actually, the ratio actually was the slant asymptote. It won't always be that way. It'll only ever give you the leading term of the slant asymptote. Sometimes the slant asymptote is shifted up. Like for instance, if I just took this whole thing and shifted it upward, now I've got a slant asymptote, but the slant asymptote is 1x plus 3, and that's because the whole graph was shifted up as well. So then how do we get the actual slant asymptote? To get the actual slant asymptote, you get to do long division with these two terms. So you would do, what is x squared minus 1 go into x cubed plus 1? And folks, it would be helpful to go ahead and put in those extra terms. 0x squared plus 0x plus 1. So let's go ahead and do this. Practice long division with me. Now you only have to do long division if the power on top is bigger than the power on bottom. That's it. If the two powers are the same, it's horizontal asymptote, not a slant asymptote. So we're just looking at slant asymptote. Okay, so it works like this. What do I multiply by x squared to get x cubed? Just x. So then I multiply x times x squared is x cubed. X times negative 1 is negative 1x. You'll notice I just put in the 0x squared term. I suppose we could go ahead and put a 0x term in here. That might make it easier. X squared plus 0x plus 1. There. Okay, so in normal division, you multiply, and then what do? You subtract. So what I'm going to do is change all the signs. So that becomes negative, that's still 0, and then becomes plus. Now I can add, so those cancel out. Those are nothing. And here I have 1x. And then I drop down my next term. Now, when you do long division with algebraic expressions, you keep going until you can't go anymore. So right now, if I ask the question, x squared times what gives me x? There's no answer. So this is the slant asymptote, right there. Whatever you get up top from your long division is the slant asymptote.
We have to figure out it, we also figure out everything else.
Yeah, and then you would proceed to figure out everything else. That's, well, I mean, technically you'd call that one of the 1x plus 0. But yes, just x. So there's our slant asymptote. But yeah, what else can we do? I think the top actually does factor. No. It doesn't. Are we sure? I think it factors. I think x cubed plus 1 factors. I think it becomes x plus 1, x squared minus x plus 1, and then all over x plus 1, x minus 1. Did I just make that up? Or does anyone else agree that it does factor to that? Same concept. Yep. Now, how did I know that that factored? Well, one rule that you learned in Math 120, which none of you took, right? Okay, there's something called sum of cubes or difference of cubes. And the sum of cubes, I'll make that x cubed plus a cubed, becomes x plus a, same, and then x squared minus ax plus a squared. That's just a rule you learn. And then the difference of cubes becomes x minus a, x plus ax. It comes out. I mean, this is kind of like memorizing the difference of squares. It's just something you memorize. If you had x squared minus a squared, we all memorize that it's x plus a, x minus a. So I tell you what, you don't need to pressure yourself to know this. I won't use this on the test. But in any case, it did factor, and therefore what happens? That becomes a whole, and we're left with that. So our problem would be x squared minus x plus 1 all over x minus 1. And so what would we expect to find? We have a vertical asymptote down here.
True.
Yeah. And then this top one actually has no x-intercepts. X squared minus x plus 1, if you graph it, the parabola is floating above the axis, so there are no x-intercepts. We can find our y-intercept. The y-intercept, we plug in 0, so the y-intercept would just be 0. 1 over negative 1. Negative 1. So let's start making a little graph and we'll compare it real quick. So our y-intercept is at negative 1. We had a hole at negative 1. So we're just going to write hole. We had a vertical asymptote at 1. And we had a slant asymptote at, oh, there it is, 1x plus 0. So we had all that so far. And I think because we already looked at the graph, don't we know what this looks like? We had a swoopy up here, a swoopy down here. I won't give you, well, no, the slant asymptote on this one was quite nice. I think I would give us all a different slant asymptote problem, but let's check. Is that what we got? Yeah, and was there a hole at negative 1? Oh my gosh, it actually showed it. Yeah, so there was our hole, which I suppose I should put. Oh, so that wasn't an X. Oh no, the hole was down here at negative 1. There we go. Letty, what's your question?
Oh, no, I can't see.
Oh, up there you go.
Thank you.
Okay, let's do one more, and we can either do 5 or 6. Which one should we do? Is anyone really excited?
5.
I'm sorry. Oh, I heard a vote for both. Number 6 is a little harder. Why is number 6 a little harder? Yeah, it's got the number on the x squared. Therefore, we should do number 6. Because number 5, I think you all could do. So let's take a look at number 6.
Are we sticking it or together? Or?
I tell you what, folks, you can all just cross out number 5. So number 6, we have 3x squared minus 5x plus 2. Didn't we already factor that once today? Over x squared minus 9. So we would have to factor the top and the bottom. The bottom is pretty easy because it's the difference of squares, so that's just x plus 3x minus 3. And now the top, you would factor in whatever method you want to use. I'm going to rewrite the middle term, so I've got 3x squared minus 5x plus 2. And I know, so 3 times 2 is 6, and that's either 1 and 6, 2 and 3. They have to add up to 5, so that's 2 and 3 when they're both negative. So I have 3x squared minus 2x plus minus 3x plus 2. And then factoring by grouping, keep in mind you have to have a plus. Sorry, I should slow down here. Acting like someone's chasing me. What can I factor out of the first pair? X. Yeah, so that's just x outside of 3x minus 2. What do I have to factor out of the second pair? Yeah, the leading negative. So I'll bring out that negative 1, and that also leaves behind 3x minus 2. And since 3x minus 2 is the same, our factor is 3x minus 2, and then the bits left over, x minus 1. All right, so 3x minus 2, then x minus 1. And you could just call that the front work of the problem. We haven't even started analyzing all the asymptotes, but we know we had to factor that. So should we go in order of A, B, C, D again? What is our domain? What is x not allowed to equal? Yeah, x can equal 3 or negative 3. All right?
Wouldn't one of them be positive?
Yeah. 3 and negative 3?
Or the 3x minus.
No, because you have negative 2 times negative 1, which gives you a positive 2.
Yeah, it definitely has to be negative times a negative.
And up here it's a negative 2.
You what?
The negative 2, so it's negative 2 times negative 1, that's a positive 2, right?
Right.
It's negative 2.
Oh, the equation is negative 2. Oh, I did that
it's not
whole
negative,
thing
it's not.
wrong. I did the whole thing wrong. So that's a negative 6, so that should be plus 6. No, plus 1 and minus 6. Oh, this is so sad. Thanks, Omar. Folks, I did the whole thing. Is that why some of you were looking at me weird?
Yeah.
Because I could tell the something weird happened right then. Okay, so that would really be 3x squared minus 6x plus 1x minus 2. And then factor by grouping. And then I take out a 3x, so that's x minus 2 plus 1, x minus 2. And so that'd be x minus 2 and 3x plus 1. All right. Which is totally different. 3x plus 1 and x minus 2. Okay. Thank you, Omar, for pointing that out. The domain is still 3 and negative 3. And then were either of them holes? No, because nothing canceled, so no holes. And then C, which was the vertical asymptote? They both were. So we have vertical asymptotes at the equations x equals 3 and x equals negative 3. Those are both vertical lines. And then horizontal asymptote. We look at the ratio of the leading terms. Oh, this is a good one. So our ratio of leading terms is 3x squared over x squared, which is really 3x squared over 1x squared. The x squareds cancel out, and we're just left with 3. So that means our horizontal asymptote is at the equation y equals 3. And then E was, oh, the slant asymptote. There is no slant asymptote because the power on bottom is not smaller than the power on top. But, sorry, the power on top is not bigger than the power on bottom. No slant. All right, so how do we put this together into a graph? We would have our vertical asymptotes at 3 and negative 3. And then we'd have a horizontal asymptote at y equals 3. We didn't solve for the y-intercept or x-intercept yet. So the y-intercept is f of 0, which if I plug 0 into all that, I would just get 2/9. So 2/9 is my y-intercept, which I'll just put a dot barely above the x-axis. And then my x-intercepts are in the numerator. So what are my two x-intercepts? The easy one is at 2. How do you solve the other one? Yeah, negative 1/3. You have to set this whole thing equal to 0, right? So you'd set 3x plus 1 equal to 0. And so 3x equals negative 1. And so x equals negative 1/3. So there's my other x-intercept, which is also just left of the y-axis. So that gives us 2 little dots right there. And that's all we have to go on in order to guess what the rest of this graph looks like. So can we just guess what the rest of the graph looks like? No. You can't just guess.
We put the 2 in there as well, the x-intercept 2.
Oh, yeah, and the x-intercept of 2. Thank you. So that's good. We have 3 little dots here in a row. That implies that I have some sort of upside-down graph right here. Again, that's a very weak implication. It could have looked like a lot of things. But now let's just look at the graph and see what it looks like. There was 3x squared minus 5x minus 2, all divided by x squared minus 9. There. All right. Well, do you believe it? That that's what our graph will end up looking like? We would have a swoopy up top, an upside down looking thing, and the one on the right actually comes down below the horizontal asymptote and goes back up to meet it. That's a rather unique feature. This horizontal asymptote comes down and rides along the top of it. This one came all the way down past the asymptote and then came back up to meet it. So that was interesting. Again, you wouldn't know that just from looking at the function. You'd have to actually graph it and see that kind of a subtle feature. Okay, so before we leave for break, let's just go ahead and say that we're going to do no, I think that's it. All of section 4.2 is just additional practice. So I don't think I'll do any more of section 4.2 with you because we've already essentially looked at a variety of problems like this. So when you come back from break, we're going to start back in with section 4.3. If anybody wants to stick around and ask me any questions, right now is a good time. Otherwise, go enjoy a break.
You both coming up to see me or just you? That's it. Yeah, that's it. Oh, I had the learning center, have maintenance there now. You did what? I had learning center maintenance there now.
Oh, thank you. I think I can tell the difference. It already feels better. Why don't they just already have it good?
Who knows?
So, you're getting married.
Yeah.
That's huge. I had no idea you were engaged or getting married or anything.
Yeah.
So, where are you getting married?
Over in, I believe it's Gilbert. Josiana's wedding, is what it's called. Basically, the pastor, with counseling people, and he found that, like, after everything worked out, they wanted to redo their vows.
Yeah.
So now he's married people when they want to get married. And if you, because Chris and I have been together for so long, they're not making us do this thing, but for most people, if they're trying to get married, then they make them like do counseling for 6 months or something like that.
Sure.
And then
Is that the Catholic church or what?
no, this is a regular pastor.
Oh, that's just his thing.
Yeah.
Okay. Wow, that's great. Well, I mean, it's a great idea.
Yeah.
You know, doing counseling or something before you get married to talk about big issues.
Right.
Before they come up anyway.
Because there's a big killer.
Yeah. Well, that's awesome. Well, congrats. And March 18th.
Yeah. So
that's only 4 days after Friday. That'll be pretty easy to remember. Yeah, because otherwise you'd have no other reason to remember. But hey, it's only 4 days after Friday. My nephew was actually born on Friday.
Oh yeah.
Oh, he's just so bitter. Yeah. I want one of my own kids to be born on Friday. Always. I can what?
Believe it's
Hey, we tried.
believe November 11th. There's two high days actually.
Wow.
There's March 14th, right? And then there's a second one. And it's the 314th day of the year.
Oh, it's the 14th day of the year. Okay. I wonder what time of day that would be. Because it'd be 314.159. So what time of day?
2 o'clock in the morning or afternoon.
Yeah. Well, I think it'd have to be in the morning. We're going to the decimal representation. So. So it would be. It'd be 3 a.m. That's my calculation. 3:49 and 20 seconds. Hey, I got 3:49. Not too.
Really?
Yeah.
How'd you do it?
Well, because I did 0.15926 times a 24-hour day. Because if you did it times a 12-hour day, that'd be different. Then it would be close to 2 a.m. Yeah, but I think it's only fair if you're going to express the time of day as a decimal representation. That's what I've all done before. Just really.
You have to be prefer to be a mathematician. That's good. It means it's expanding. Keep growing. Do you know what okay, so the symbol of pi, right? You know what it is for mathematicians? The number? It's like 3 point so many numbers, right? You know what pi is for the number pi is for Greek?
Really? In
Yeah.
Greek, pi is the symbol to 80?
80, yeah. 80.
Like the number 80? I'm about to look it up.
He's like, I'm gonna look it up right.
Now we're gonna, not that I doubt you, wait, by no means, but I just never heard that. Oh yeah, it says in the system of Greek numerals, it has the value of 80. Yeah. It's what, like in Roman numerals, Greek numerals?
Yeah.
I mean, that makes sense, they didn't have place value for that yet.
Right.
So it would have just, oh.
And there's not a symbol for 0 at all. So
Yeah. Huh.
yeah, because when I do my PowerPoints, I always do like a theme. And last PowerPoint or the last meeting was about pi since pi is coming up. And so it was what's the number for pi in Greek? Who was the first person to use it? I believe it was John Paul.
In the 1900s? He was possibly primary.
I had like a movie about pi, like the history of it.
Oh.
It was nice. If you guys don't have a chance, every other Thursday it is that's what our next one will be after this Thursday.
Are you guys gonna be doing it
The Wednesday, you guys. Oh, talking about that as well. We're doing voting for who gets pie in the face.
What?
Yeah, so you get a vote for who gets pie in the face. So it's gonna be 50 cents per ticket. 3 tickets for $1. You have myself, Amber, which is our president, Matt, which is our research secretary, Rachel and Shannon, which is our officers, Dr. Chang and Mr. Chang. We're going to be who you can vote for. Whoever has the most tickets is the one who gets the pie in the face.
Yeah.
Go ahead. Go ahead. See you guys.
I'm hungry. What else do I want? I remember something.
Yes. Yeah.
Oh, I remember him. I have him. Yeah, it's just for this one.
But you can vote for any of them to be pie in the face. It is 50 cents per ticket. $34. The way it's played is once you get a ticket, you put it on by number, put their name on the back.
Rachel.
And then whoever gets the most out of the area, all of it, that's the one who gets pie. Actually, we're gonna have to.
I didn't carry all these changes. I bought a book. So you already booked, I don't carry anything.
So if you guys want to do it, let me know.
Oh, my.
You will? Yeah. How many do you want?
I'll take it.
Take three?
Real?
Oh.
No, wait, is that just a vote or is that to actually put something?
No, it's the vote. Whoever gets the most tickets is the one who gets the pie.
No, it's a real one. Yeah, that birthday. Oh, really? Yeah.
Today. Put the name on each one of the back.
Nice song.
These are the names.
Yep, that's these five. Plus five
Oh,
or
that- it's just like. Thank you so much.
You have news, did you?
My lower back, just a little tight, I'm just trying to stretch it out.
You lay flat on the back and throw your hip to the side. That one.
Oh, that's a good one.
That's what I used to do when I was inside still.
You're flexible.
I am.
Yeah,
Really?
I think so.
My wife is the yoga teacher, I'm not flexible. Okay, so folks, let's try this out. Everybody back when you're Hector. Oh, that just was better.
Right back.
By the way, everybody, we did call about the air conditioning, so it should be getting cooler in here. Thank you, Lee.
Of course.
Okay, there's a couple main ideas we want to think about when we solve an equation. I'm going to put all these ideas up front so we have them in our mind as we're working. All right. So first of all, notice that when we write down something like number 1, which is x over 5x plus 4 equals 3, okay? It's an equation, quote unquote. This is an equation. However, we could just as easily look at it as a function, which is x over 5x plus 4. And we're wondering, when is the output of that function a 3? And therefore, we're asking what input would cause an output of 3. Right? So, if we think of it as a function equaling a particular output, I can then go graph that function. So, x over 5x plus 4. And then I could just ask the question, when is my output 3? And remember, output is the y value. So I could now plot the horizontal line, y equals 3, and I can just look at my graph now and say, where do those two intersect? So when is the function having an output of 3? Right there. Yes, we already know, it's just right there. And that answer, by the way, I think is negative 6/7. Just guessing. So that's one way to think of this, is that what you can do is graph the thing on the left, graph the thing on the right, and see where they intersect. This is really nice because automatically you can find the answer to any algebra problem by using your graphing tool. So how does everyone feel that you graph the function on the left, graph the function on the right, and then you just look to see where they intersect, and that tells you the answer? Okay. Second thing we want to know. Okay, so that's just one way of thinking about it. The next thing is, again, thinking about it as a function. I want you to watch this and see how neat this is. So, well, sorry, not really as a function, but just thinking about this equation, okay? I have something over 5 something plus 4 equals 3. Okay, so I've got this function. I'm going to input a number, and I want to know what number can I plug in so that it actually equals 3. And so I want you to consider this with me. There are numbers I can plug in that will make this true. That statement could actually be true if I plug in something. So I'm guessing that there's at least one number in the world. We already know there is. It's the number negative 0.857. This expression will be true if I plug in a certain number. This expression will be undefined if I plug in a certain other number. So for instance, what number can I not plug into the denominator? I don't want the denominator to equal 0, right? So first of all, let me put down the answers. The first answer was negative 6/7. So if I plug in negative 6/7, this whole thing becomes true. If I plug in, let's see, I don't want 5x plus 4 to equal 0. So that means I don't want 5x to equal negative 4. Which means I don't want x to equal negative 4/5. So this whole thing will become undefined if I plug in negative 4/5. And finally, this expression will be false if I plug in anything else in the universe. Okay, so this is really interesting. We're basically saying that going forward with all rational equations, you can plug in basically any number you like. And depending on what number you plug in, the whole expression will either become true if you plug in just the right number, or the whole thing will become undefined if you plug in the number that makes the denominator 0, or the whole thing will just be false if you plug in anything else. This is really interesting to notice because how many numbers can I plug in to make it true? Just one. How many numbers can I plug in to make it undefined? Just one. And how many numbers can I plug in to make it false? Infinitely many. So it's kind of sad, really, that most equations spend the vast eternity of their lives being false. Right? For the most part, an equation is false. It's only just for this momentary blip. It's true if you plug in negative 6/7. And just for one little blip of its existence, it's undefined if you plug in that number. But all the other numbers you plug in, the equation will be false. I don't know, that's enough to make me just sit down and shed a tear for equations. That for the most part, equations are false. And if you just plug in random numbers, equations are false. It's only certain special numbers you can plug in that will make it true. And we call those numbers solutions, right? Okay, so having all that under our belt now, that we can look up the answer to any equation by graphing it, and that we're actually interested in 3 things. Well, we're really interested in 2 things. When is it true and when is it undefined? So moving forward, everybody, let's do number 1 together now. Yeah, because we didn't solve it yet. We're always going to ask ourselves first, what is the domain exclusion? That's the first question. What can't x be? Yeah, and then the second equation is, what answer should x be? Right? That might feel a little weird, but the first thing you want to know is, what shouldn't you plug in for x? But then we'll ask, what should you plug in for x? So everybody go ahead and take your x over 5x plus 4 that equals 3. And the first thing we're interested in is our domain exclusion. Domain exclusion. So we're saying I don't want the denominator to equal 0, which means I don't want 5x to equal negative 4, which means I don't want x to equal negative 4. So right up front, I know I'm not even allowed to plug negative 4/5 into this function, because then it would be undefined. And what you'd really have then is undefined equals 3. And that's not a true statement. Okay, so now we're going to solve. So how do we solve x over 5x plus 4? Because you'll notice we have an x in the numerator and in the denominator. What do we do?
We put the 3 on the other side of the 1. Or thinking you multiply the denominator times itself and then multiply it by the on the other side.
We are going to do that.
Okay.
We're going to multiply both sides times 5x plus 4. And I just want you to I want you to be motivated for that. What if the problem was just x over 5 equals 3? How would you solve for x? You multiply by 5. And if you do multiply 5 on both sides, what happens to the 5 over here? Yeah, it just cancels. So when I say, what should we do to the 5x plus 4? Our actual goal is to cancel it. And in fact, in general, every single rational equation that you ever see, your first goal is to cancel the denominator. To destroy the denominator. Like when somebody says, how do you solve equations with denominators? Your answer is you destroy the denominator. You get rid of it. And then you solve whatever you have left. Okay, so let's do it, folks. We're going to go ahead and multiply both sides times 5x plus 4. And that's nice because it just immediately cancels the 5x plus 4 on the left. And then we just have x equals 3 times 5x. And then what? You distribute. X equals 15, x plus 12. Now, typically what I like to do is I move all my x's to the left and I move all my numbers to the right. But other times, I think it's better to move my x's to the right because that way the x stays positive. So honestly, you can do it either way. Right now, I think I will move the 15x to the left because then I have all my variables on one side and my numbers are on the other side, and I'm ready to divide off the negative 14, and then I'm done. So x equals negative 6/7, which you'll recognize was the answer we said it was from the decimal on the graph. But recognizing the decimal, 0.857 to be negative 6/7 is a little tricky. That's why you want to do the algebra to actually get the correct answer.
Mr. Chu?
Yeah.
Do you want them to do it just like that when they do the division?
What?
Like the negative 14 divided by negative 14. The reason I'm asking is because when I do it,
yeah.
I multiply the entire thing, the last step, I multiply it all by negative 114.
Oh, you multiply by the fraction?
Yeah.
Oh, it's fine. Otherwise, it's fine.
Okay.
Yeah. All right. Well, folks, we've done it. In this particular fraction or this particular equation, then we would have 3 answers. We'd say true if x equals negative 6/7, undefined if x equals negative 4/5, and false if anything else. Isn't it the first time anybody's ever asked you to list 3 answers? No, you've seen that before? Or you've done that before, where you list out when it's true, when it's undefined, when it's false? Okay. I mean, it's one here?
Yes, someone asked us to do 3 answers.
Oh, okay, great.
It's just I've never seen that this way.
Oh, okay. Well, then that's fine. I mean, it's nothing official. It's just I want us to think about it. I just want us to think about all the possibilities. All right. So, what have we taken away from that? We have an equation. It has a denominator. What's the first thing we want to do to the denominator? Cancel it out. Just get rid of it. But before we can do that, we really need to do our domain exclusion first. So we would look at an equation and say, well, I don't want the denominator to equal 0. So first I'll do my domain exclusion. And I'm going to say, I don't want x squared plus 1 equals 0. In this case, x squared plus 1 will never equal 0. Because x squared is a square number, which is a positive number, and a positive plus a positive will never be 0. So there are no domain exclusions. You can plug any number in the universe into this, and the denominator will never equal 0. You can see that by solving it. You go ahead and solve it algebraically. You get the solution, x equals I. So the only number that actually you could plug in to make the denominator 0 is an imaginary number, and we don't care about those anyway. Furthermore, if you just look at the graph of x squared plus 1, you would see that the graph is floating above the axis. There are no x-intercepts. So once again, there is no number that you can plug in to make this thing equal 0. Okay, so there's no domain exclusion. X can be anything you want, and this thing will be defined. Then now we just have to solve for x. So 3x minus 1 over x squared plus 1 equals 1. And again, we're going to multiply both sides by the denominator. Again, we do that to immediately cancel the denominator. This is kind of funny. Like, okay, I have an equation with a denominator. How do I solve for x? The answer, get rid of the denominator. So like you go home, you're like, I have to back into that solution. I'm not going to back in. That would make no sense. And yet in math, it makes perfect sense. That denominator makes things hard. I'm going to destroy it. Okay, so then what do we have? 3x minus 1 equals x squared plus 1. It's true though, if you went home and broke your vacuum, you can't vacuum today.
That's answered all I've.
Yeah. Yeah, so store that one. Okay, now, this is a different situation. You can't just say bring your x terms to the left and your number terms to the right. From here on in, if it's an x squared, x cubed, you always put all your terms on one side and 0 on the other. So since x squared is already positive on the right, I'm going to leave an x squared on the right and send everything over to the right. So I'm going to minus the 3x to this side, and then add the 1 to this side. The way those cancel out, I have 0 equals x squared minus 2x plus 1. Now, whether you move everything to the right or everything to the left, that's up to you. But it definitely has to equal 0. Why does it have to equal 0?
Because you have 2.
Minus 2?
Oh, I'm sorry. You're right. All right. Yep, because that didn't cancel out. So that would be x squared minus 3x plus 2. There we go. One more. Thank you again. Okay, so why do I need it to equal 0? Because we're about to use the zero product rule. So in general, you need all of your terms on one side equaling 0 on the other, because that way you can do factoring and then zero product rule. So now we know that x equals 2 and 1. You all get the same answers. 2 and 1. Okay. Okay, so back to the beginning. We started by saying I want to solve this equation. That means find the numbers I can plug in to make it true. We're not technically done until I plug the numbers in to see if it's true. So I have my equation, 3x minus 1 over x squared plus 1 equals 1. So first I'm going to plug in 2. So 3 times 2 is 6, 6 minus 1 is 5, over 2 squared is 4, 4 plus 1 is 5. And indeed, 5 over 4 is equal to 1.
It's true.
Yeah, it's true. Then I'll plug in 1. So then 3 times 1 is 3 minus 1 is 2, over 1 squared is 1 plus 1 is 2, and indeed, 2 over 2 is equal to 1. So they're both true, and they're both my solutions, and now I'm truly done.
Truth is satisfying.
Truth is satisfying. That's, I mean, plugging a number back in is the most satisfying part. All right.
We have to check them, or are they always going to be true?
That's the thing, they're not always going to be true.
That is not the most satisfying part.
We have to check.
Yeah.
The most, even if you plug the number in, you don't know if it's right until you check it.
Yeah. Oh, you mean by looking here?
Yeah, that could have been wrong.
It could have been. Yeah, it could have been, but fortunately it turned out to be right. Okay, now, yeah, we do have to check. Now, here's why. Because when we did our domain exclusion on the first problem, we found out that x couldn't be -4/5, and then we solved it to be -6/7, and we were fine. But sometimes you'll say the domain exclusion is -4/5, and then you do the answer, and the answer is -4/5. And that's a direct contradiction, and therefore you'd say there's no solution at all. In this particular case, in this one, there was no domain exclusion, so both of our answers are valid. But you see, sometimes we're going to do an analysis, and I'm just going to pretend like this is number 11. And then the domain exclusion would be x can't equal 1. And yet, when you do your solving part, you're going to get x equals 1 and 2. And then you'd say, well, darn it, it can't be 1. So you eliminate that answer choice, and you say there's only one answer, which is a 2.
You always want to check it.
Yeah, you always want to check it. Omar, does that answer your question?
Yeah.
Yeah. So you're always checking your solution against your domain exclusion to make sure that you don't have to eliminate any answer choices. And when you do eliminate an answer choice, there's a special word for it called extraneous. Extraneous means that the algebra took you there, but the domain exclusion took it away. Okay, so now let's go ahead and see one of them. We'll go ahead and do number 3. Ah, yes, number 3 looks good. So I'm going to come over here. All right, 1 over x plus 3 plus 1 over minus 3 plus x squared minus 3 over x squared minus 9. So we're just looking at this problem, and again, we're asking ourselves, what number can I plug in to make it true? That's what I want to know. What number can I plug in to make it true? Second question, what number can't I plug in? Because it would be undefined. So we can do our domain exclusion very quickly. What number can't we plug in? You're going to look in the denominators.
X minus 3, X plus 3.
Yeah, so you can't plug in -3 or +3. And in fact, this last term, this x squared minus 9, that actually factors into x plus 3, x minus 3, which is the exact same two terms. So overall, we know that our domain exclusion is -3 and 3. So we know for sure that we can't plug in 3 or -3, but we're still wondering what number can I plug in? You think 4 is the answer? Oh, yeah, you can. Yeah, sure. You can plug in anything else. And for the most part, whatever else you plug in will make a false statement, but there should be at least one number that you can plug in to make a true statement. Okay, so now what do? We already said what our number one goal is. When you're given an equation with denominators, your goal is to cancel the denominators.
Yeah.
Sorry, I asked my question strangely. Yeah, we already figured out what we can't plug in. But if you want to do algebra and solve an equation with denominators, your goal is to cancel the denominators. Okay, so the quickest way to do that is to multiply through all the way with the common denominator. But let's look and see how that works first in an example. Let's say that we had the problem 1/3 plus 1/5 equals x/15. Okay? And I don't like that there are fractions. I like to get rid of all the fractions. Well, first of all, what's the common denominator of 3 and 5? 15. So what I'm going to do, and folks, I want you to watch, is I'm going to just go ahead and multiply all the way through by the common denominator of 15. What will happen if I do? This would become 15 over 3. And this would become 15 over 5. And this would become 15x over 15. And so what's the result of multiplying through by the common denominator? All the fractions go away. And that's our goal, is to get rid of all the denominators. And so you can cancel all the denominators by multiplying through by the least common denominator. Okay. One other thought about that is that this 15 is really 3 times 5. And so what you're really doing is you're saying to yourself, the least common denominator are those numbers that they all have in common. So ideally, what we want to do here, if you actually did create a common denominator, so one more thought here. If we actually did create a common denominator, this denominator has a 3, but it doesn't yet have a 5. This denominator has a 5, but it doesn't yet have a 3. And this denominator already has a 3 and a 5. So what do I want to contribute to this fraction? I want to give it a 5 on top and bottom. What do I want to give to this fraction? A 3. And this fraction already has it in it. Right. And now I actually do have a common denominator, which is 15. And so that's just 5 plus 3. And over here, that's also 15. Okay, yeah, so that'd be 8/15 equals x/15. And therefore our answer is, you'll notice once the denominators are the same, you can just equate the numerators. That's what the answer is actually in that case. So again, what we want to do then is think, what is the common denominator? And then multiply all the way across so that you cancel all the denominators. So let's try that, folks. I'm going to do this in 2 steps so that we all see it. First of all, what does this fraction also want in its denominator? It has an x plus 3. It wants an x minus 3. So I would go ahead and contribute an x minus 3 to the top and bottom. Like that. Now it has both denominator terms. What does this fraction want? It wants an x plus 3 on top and bottom. So I would do that. And now, do they all have the same denominator? They do? Yeah, they all do. So now I can say this fraction is just x minus 3 over the common denominator. This fraction is just x plus 3 over the common denominator. And this fraction is x squared minus 3 over the common denominator. And once they all have a common denominator, what can you do? You can just focus on the numerator. Now that's one way of looking at this problem. Okay? So from here, I can move on now and just say x minus 3 plus x plus 3 equals x squared minus 3. That might feel weird. We just ditched the whole denominator. Yeah, and then we'd say, well, that's a x plus x, that's 2x. The 3's cancel out. And so now we have 2x equals x squared minus 3. Again, we need all the terms on one side. So I'm going to move my 2x over. And that gives me x squared minus 2x minus 3, which factors into x minus 3, x plus 1. And therefore, the solutions are 3 and negative 1. Now, what I just showed you right here is what I would consider like the reasonable approach to this problem. You know, finding a common denominator, because that's how you add fractions. You find a common denominator. And so I found a common denominator, and then I set the numerators equal to each other, and I solved. This is just one approach to doing a problem like this. Now, first of all, let's compare. Our answer is 3 or negative 1. So I'm going to write these down side by side. I said the answer was 3 or negative 1. But we previously said that x couldn't be negative 3 or 3. And therefore, this solution right here is extraneous. You know, we never use the word extraneous in common society, so you could probably just start using it any way you like and no one would know any different. You could be like, hey man, don't be so extraneous.
In mathematics society, how does that work?
Well, if you're at a math party, people would know what extraneous would be. Or you could be like, hey, looking mighty extraneous today. And you're like, what does that even mean? Nobody knows, because nobody knows this word. David?
It sounds like strenuous, like strain. Not anything like that.
Strain?
Like,
It's like I strained my back?
something strenuous. Yeah.
Oh, I don't. Extraneous? Intraneous?
Out of shape.
Yep, out of shape, is that what you said?
Look it up. I don't know.
Yeah, you look it up. So in any case, what we know now is that x equals negative 1 is the only actual solution. There's only one number in the universe that you can plug into this thing to make it true. And the answer is negative 1. Okay, so if that's what I would call the reasonable approach to this problem, find a common denominator and then set the numerators equal to each other, there's another method that the book teaches, which is a very good method, and I want you all to know it. And we'll practice it a couple times.
I think I was saying it wrong. It's strenuous.
Oh, strenuous. Yeah,
It's
yeah.
not the same.
Doing math is very strenuous.
Yeah, that's why I was like, that sounds so familiar.
Yeah.
It's just means stress, doesn't it?
What's
Uh,
that?
Strenuous means stress.
It says requiring or using great exertion.
Okay, folks. I will beg your patience, and we'll do number 3 again, but differently. So let's see the other way to do this problem. And you're going to really like this, so definitely write it all down. Don't just watch it right now.
Are you gonna do them?
Yeah, we will. Oh, then we're out of space. Well, then you actually only have to write down the first 2 steps of this one. Well, okay, I see you are totally out of space. Maybe a sheet of line paper then, or maybe if you turn it over, we didn't do anything on the backside. Oh, if I can turn the page, which I cannot do. Oh my gosh. Just be aware for that when you can't. That the pages are separate. Okay, so what can we do? First of all, the x squared minus 9 factors, and we have 1 over x plus 3, 1 over x minus 3. And then x squared minus 3 all over plus 3 minus 3. So what was the common denominator again? We found it. The common denominator was?
X minus 3, x plus 3.
Yeah, the combo of both of them. So what we'll do is we're going to multiply x plus 3, x minus 3 all the way across. Now, when you actually do that multiplication, it gets worse before it gets better. So I'm going to multiply times 1, so that's 1 times x plus 3, x minus 3 all over x plus 3. And then I have 1 times x plus 3, x minus 3 all over x minus 3. And then I have x squared minus 3 times x plus 3, x minus 3 all over x plus 3. So at first glance, it looks terrible. Yeah, it is helpful to see. So all we did was, first of all, we followed a valid algebraic rule. We multiplied the same thing on both sides of the equation. That's why we're allowed to do that. Because I multiplied the left-hand side by the common denominator, I multiplied the right-hand side by the common denominator. And now, after you spent all the time and effort to write all that down, what glorious thing do you get to do? Yes. Yeah, you get to cancel so much. And what do we end up with? We end up with the exact same thing we had in the previous problem, which is the numerator plus the numerator equals the numerator. So you can see at this point we got right back to just the numerators.
You feel satisfied, like, do you feel satisfied when you do that part?
Oh yeah, always. Canceling things is always very satisfying. That's like after you vacuum and you get to cross it off your list. Okay, we don't have to finish it because it's going to be the same solution now. I just wanted you to see what it looked like to multiply to multiply all the way through by the least common denominator.
I heard somewhere that you're not able, I guess the way it's just the way it's written, but you aren't allowed to do factor with the equal sign in the way.
Huh?
It's the same thing, but it's just the way it's written out.
What are you talking about?
Well, the way you distribute it, I heard that you can distribute between.
Oh, across an equal sign?
Yeah.
That's fair. Technically, I should have multiplied the left-hand side by that, and then the right-hand side by that. Yeah, is that what you mean, Hector?
Yeah.
Yeah, that's fair. Yeah. Yeah, because technically what you're doing is you're multiplying both sides of the equation.
Yeah.
Okay. Well, folks, let's move on and check out number 4.
One thing you'll find out, Hector, is that mathematicians are very lazy.
I know that. Which is an interesting paradox, because on the one hand, lazy, on the other hand, not at all lazy. Because we're willing to do all the work that most people are going, I don't want to do that problem.
You're going to say that effective or say effective.
Well, I kind of cut a corner there, right? By not writing it on both sides. Is that what you're saying, Hector?
Efficient.
What is it?
To be more efficient.
Oh, I suppose, yeah. Yeah, like not wanting to actually write it on both sides. Okay. So again, from the big picture, we're looking at this equation. We say there should be a number I can plug in to make it true. There's a number I can plug in to make it undefined. And every other number will make it false. Yeah, well, first let's look at our domain exclusion. Just so we know right up front, what number can't we plug in? Yeah, x can't equal -1. So I know that can't be a solution. Because if I did plug in -1, it'd be dividing by 0, and that'd be undefined. Okay, so yes, you have an equation with a denominator. You want to cancel your denominator. So we're going to multiply both sides by x plus 1. And you'll notice we did, in fact, just multiply by the least common denominator. What would be the common denominator of these two fractions? X plus 1. And so we're multiplying that on both sides. Actually, I'm writing it on both sides.
I'm not saying.
No,
I'm not saying it's wrong. Write it that way. I'm just saying.
Right,
That's a rule.
Yeah, and I agree with you. So now it cancels on the left, and we have 2x plus 17 equals x plus 5, x plus 1. Now notice, the way we have it written right there, is anyone tempted to use the zero product rule right now and say x equals -1, x equals -5, and x equals -17/2? Oh, good. Why aren't you allowed to use the zero product rule? Because it has to be equal to 0. Yeah, you can only use the zero product rule if it's equal to 0. And right now, we have a long way to get there. Well, not a long way. So what would we do? Yeah, we'll have to FOIL that out to get x squared plus 1x plus 5x plus 6. Sorry, plus 5. And then we'd have x squared plus 6x plus 5. All that equals 2x plus 17. And we do want all the terms on one side so that it will be equal to 0. So I'll move my 2x over and move my 17 over. So that now I have 0 equals x squared plus 4x minus 1. And now we are allowed to use the zero product rule. Because the whole thing is equal to 0. What multiplies to make 12 that adds to make 4? Yeah, 6 and 2. So x plus 6 and x minus 2. And now we can use the zero product rule. We say x is either negative 6 or 2. And that does not contradict our domain exclusion. That does not conflict with our domain exclusion. So in this particular case, we can plug in negative 6, it'd be true. Plug in 2, it'd be true. Plug in negative 1, it'd be undefined. Plug in anything else, it'd be false. Have I plugged either of these in yet? So I should not have any confidence that I'm right yet. I could have made a lot of mistakes. I could have just lucked out to make enough mistakes that it still factored nicely. And I could have a false confidence right now that those are my solutions. I only know those are my solutions after I plug them back in. So I'm going to plug in negative 6. So if I plug in negative 6, that'd be 5 over negative 5, and then negative 1. And it works. Negative 1 equals negative 1. Now I just did all that in my head. Right? So I mean, when you plug the number in, you can do it any way you like. You can plug it in your calculator. You can show enough work to actually get you there. Like if I plug in negative 6 plus 17 over negative 6 plus 1, I could do all my work and slowly but carefully get myself to the answer 5 over negative 5 equals negative 1, negative 1 equals negative. Again, you can show as much or a little work as you like to show right here. The main thing is you want to convince yourself that it's true. So now I'll plug in 2. So 2 times 2 is 4 plus 17 is 21, over 2 plus 1 is 3, and then 2 plus 5 is 7, and turn out 7 equals 7. I just took a test over the weekend for my math class that I'm in, and I checked every single problem because I wanted to know that I got it right. What? The course is called Optimization Techniques. Titles, they don't sound nearly as exciting, but it's mostly matrix algebra, so using matrix. Okay. What's that? Right. I forget which one is which, but I'll take truth. Oh yeah, not that matrix. Yeah. Okay, we have a couple more problems here to try, and then we can look at some inequalities. Now, once again, I want to go back to this idea that we could find out the answer right away. Like here we have this equation, number 5, and I'd like to know, is there a solution? Like I'd like to just know right away, so I can just graph it. I'll graph the left-hand side, so x squared minus 2x plus 1 divided by x cubed plus x squared minus 2x. And I'd like to know, when does that intersect with the horizontal line y equals 1? So folks, where does my purple graph intersect my black graph? It doesn't. So that means that 1 will never be an output of that function. Provided we trust the graph. Maybe you think you have to zoom out more. But no, the black line is never going to intersect the purple line. So this equation has no solution. That's nice to know up front, but we would still want to do an analysis. So let's do it. So we have x squared minus 2x plus 1 all over x cubed plus x squared minus 2x equals 1. So if we ask the question, what number do I plug in to make this thing true? The answer is there are none, because we already looked at the graph. But if we ask, what numbers can I plug in to make it undefined? This thing could be 0. Especially if you let x equals 0. So I already know that there's at least one value where it's undefined. And finally, we want to solve the equation, which means we have to get rid of the denominator. And how do we get rid of the denominator? Multiplying by the denominator. So over here on the left, I'm going to leave it blank. I know what I'm multiplying by. And over here, I'm going to multiply by x cubed plus x squared minus 2x. So over here, those just cancel. And I'm left with x squared minus 2x plus 1 equals equals x cubed plus x squared minus 2x. What do we do? Yeah, Omar?
Could we factor our next from the
Yeah, we can. And in fact, I skipped right over the domain exclusion. Should we go back and do the domain exclusion, or should we finish doing the algebra? We have to do both. We do have to do both. I got so excited, I just started doing the problem. Let's finish the problem. So I already have my x cubed term over there on the right, so I'm going to move everything to the right. So I'm going to, oh, in fact, what can I cancel from both sides, folks? The x squared cancels from both sides. The 2x cancels from both sides. So now I just have 1 equals x cubed. And so if I subtract that over, well, actually, no. We're ready to solve. 1 equals x cubed. How do you solve for x?
Square.
Just 1. X is being cubed, so you cube root. Now, good question. How do you cube root? You might know the cube root of 1 off the top of your head. What number times itself 3 times will equal 1? 1. But what if you didn't know? What if you needed to find the cube root of 17? How will your calculator do that for you? Do you know where your cube root button is? Under math. Everybody want to look? Under math, you just go a couple options down, and there's the cube root. That's the math button. Did everyone find their cube root button? Did you find it? Okay, great. Omar, you have one of these, right?
Yeah.
You just didn't bring it today. Hector, do you know where the cube root button is? Dave, did you find it? Under math? Yep, math.
Oh, yeah.
Okay.
Yeah, right there.
Yep, there you go. Math. And there it is, cube root. Oh no, there it is, cube root. Okay, so that's how we know the cube root of 1 is equal to 1, and therefore there's the solution that we think it is. Meaning if I plug 1 into this, it should be true. But again, we haven't done our domain exclusions yet. You need the domain exclusion to make sure that that'll actually work. So now let's take x cubed plus x squared minus 2x and say I don't want that to equal 0. So what can you factor out? An x, first of all, so that's x squared plus 1x minus 2. I don't want that to equal 0. And can I factor this? You can. 1 multiplies to make 2, that adds to make 1. Yeah, x plus 2x minus 1. So we have a triple product for a 0 product rule stating that I don't want any of those to equal 0. So x had better not be 0, x had better not be negative 2, and x had better not be 1. So you can see that in this case, there were more numbers x couldn't be than there were that x could be. And the one value that we found for x could be directly contradicts what x can't be. And that means no solution. So we would say that this solution is extraneous. Well, this solution is extraneous. It doesn't actually solve the equation. I just thought of a, well, I'm going to call this a funny joke. I don't know if any of you would think it's a funny joke. But let's just say I have the parabola x squared plus 5x plus 15. And we look at that wrong parabola. X squared, I meant plus 8x. There we go. So x squared plus 8x plus 15. And I have 2x-intercepts, right? Everybody would agree. This parabola has 2x-intercepts. So you know what I'm going to do? I'm going to multiply it by x plus 3 divided by x plus 3. And then I'll multiply x plus 5 and x plus 5. And look what cruel thing I just did to my parabola. It's still the exact same parabola. However, there's no x-intercepts anymore because I removed them. That was kind of funny. Like, anyone would think, hey, yeah, this parabola will have 2 x-intercepts. And then I'm like, nope. I removed them.
You know what? That would be would be funny if you put that question on the test.
Yeah.
And you said you can't use the calculators.
Right. Wait, if you couldn't use calculators? Why?
How would you figure it out?
Well, yeah, we would know what it is. No, all of you can figure it out. I have full faith all of you can figure it out, because if I gave you that problem, first of all, what would you immediately do? You would cancel all those things, right? So you would immediately cancel out the x plus 3, x plus 5. And then, but it is still funny. So even after you cancel out the 3 and the 5, then this one you factor into x plus 3, x plus 5. And then you'd say, aha, x equals negative 3 or negative 5, except I just canceled them as wholes, so x can't equal negative 3 or negative 5. And then exactly what you think is the answer isn't the answer. And then you'd say no solution, because they're all extraneous. So that could be that'd be another way to use it, like, oh man, I've been having an extraneous day. Like everything I've tried has failed. I don't know. That probably wouldn't be the right use of the word. Okay, folks, what do you say? I think maybe we're done practicing these, or should we try one more? You want, Emily? One more?
I'm just kidding.
Oh, no, it could be fine. I mean, there's only one more in the section, and then we're going Wait, what, Emily? I missed it. Okay. Well, I tell you what, the next 4 problems that we're going to do are more practice anyway. So let's go ahead and be done with that section.
What about number 6?
You can just cross it out. Okay. These next 4 questions are really fun, if you believe that. You know, if I say it's fun. Now, what are they really asking? It's giving you a rational expression, and what are they all setting equal to? 0. And in fact, they're setting greater than 0 or less than 0. Now, what did we learn before? If you ask when is a graph greater than 0, you're asking when is it? What? When is it?
On or
Above the x-axis. Yeah, and if you set an equation less than or equal to 0, you're looking for when it's below the axis. So we're going to just solve these problems graphically, because they're setting it up in a way that's very graphical. They're saying, when is that first equation greater than 0? That means, when is it above the x-axis? And the next one, number 8, says, when is that expression less than 0? That means, when is it below the x-axis? So let's look at the first one, 1 over x plus 2. And they're asking the question, when is it above the x-axis? And when we ask the question, when, that means in interval notation according to the x-axis. According to our x values, when is the graph above the x-axis? So first things first, folks, let's make a graph. You can draw a graph on your own paper. And let's find all the key details of that graph. So this is number 7. And we have a vertical asymptote at -2. And we have a swoopy on the right and a swoopy on the left. And notice we're asking the question, when is 1 over x plus 2 greater than or equal to 0? So visually, when is the graph above the x-axis? Just this part, right? Now, furthermore, that's just greater than 0. Is that ever equal to 0? Does this graph ever touch the x-axis? No. It approaches it asymptotically. It never touches. So we're only really saying, when is 1 over x plus 2 greater than 0? So when is it above? From where to where? Yeah, -2 to infinity. And that'd be your answer. If you wanted to make a number line real quick, you could say from -2 to infinity. And then, furthermore, is it a closed circle or an open circle? It is open. Why? What happens if you actually plug -2 into this equation? It'd be what? If you plug -2 in? It'd be undefined. And undefined is not greater than 0 or equal to 0. Undefined is undefined. So it's an open circle, and therefore our answer is -2 to infinity. So in this equation, where it says solve, it means, and you express your answer using interval notation, there are infinitely many answers. If I plug in the number, let's just try. If I plug in the number 1, 1 over 3 is a third, which is bigger than 0. If I plug in the number 2, 1 over 4 is a fourth, which is bigger than 0. I can plug in 3, 1 over a fifth, or 1/5 is greater than 0. And so on. I can plug in every positive number. But I can also plug in these numbers over here. Yeah, even 0 and -1.
So the line will never touch.
Right, the line will never touch.
But I thought if it was greater or equal to, it was on the line.
Well, the question is saying, when is the graph above the x-axis or equal to the x-axis? And the or in this case is vacuous. It doesn't exist. Yeah, when we're saying when are you above or on, the answer is it's above, but it's never on. Yeah, because it doesn't touch. Okay, nice. Let's look at number 8. Again, we're solving these graphically. So you would use your graphing calculator to solve this. You would type in x minus 3 divided by x plus 2, and you'd look at it and you say, when is it below the x-axis? And I'm going to help us out by typing in the negative or the vertical asymptote. So when is this graph below the x-axis? Is that fair that this is the only space where it's below?
Yeah.
Everywhere else is above. So what value is this? -2. What value is this? Yeah, so we know it's between -2 and 3. And now the question is just open circle or closed circle. So start by drawing a picture of our graph, and the vertical asymptote is at -2. Yep. And then the x-intercept is at 3. And our graph goes like that. So that's the only chunk of the graph that's below the x-axis. However, the question says, when is it below or on? So the question is, x minus 3 divided by x plus 2 is less than or equal to 0. So Omar, this actually covers the equals part. So when is it below? It's below between -2 and 3. So I can start my number line and say between -2 and 3, it's definitely below. So definitely that part is below the x-axis. But then there's a separate question, when is it equal to 0? When is the graph on the x-axis? At 3. So 3 is actually a closed circle. So that'd be a bracket. So the answer would be -2 to 3. Omar, does that answer your question?
Yeah.
About the either or?
I started always with that there was a point always on the line.
I see. Yeah, sometimes yes, sometimes no. Questions about that? Valerie? Is that okay? Emma? No as in no questions? Oh, okay. Nadine? How do we do number 9? Well, I'm suggesting in these problems that you would always graph to just look and see. So in this particular case, we're wondering when is it above the x-axis? So looking here,
It's a union.
what's that?
It's a union.
Yeah, it's a union. There's 2 different pieces. So I want to put in my vertical asymptotes. They're at -1 and they're at 1. That way we can just see it a little easier. So when is it above? Yeah, that's what we're asking. When is it above? So
-1
yeah, between here and here, the graph is above. And then from here and here, the graph is above. Right? From here to here, it's below. And from here to here, it's below. So we're just looking from -1 to 0. And then again, from 1 to infinity. And again, I would make a nice little graph of that before getting too far. I'd say, okay, number 9, I had a vertical asymptote at -1. Then another vertical asymptote at 1. And then, I guess that's it. And then we're asking, when is x over x squared minus 1 above 0? So I had part of my graph, well, yeah, I'm going to graph the whole thing. So I've got this swoopy. I've got that. I've got that. I'm going to trace in blue where it's above. So it's above from here and here. And then I'm not above when I'm on the x-axis. So I'm going to leave that as an open circle. Okay, so that leaves our intervals from -1, 0, 1 to infinity. So far, if I just put in a bunch of open circles, I'm looking at that interval, and I'm looking at that. That's infinity. So the question is just, do I have to make any of those open circles closed circles? And first of all, the question is, when is it strictly above? So I never want to be on 0. So already these are all just going to stay open circles. So then with a union, that'd be what? -1, 0, union 1, 2, 3. The last one is really exciting. So for the last one, folks, you can go ahead and start factoring the top and bottom because we do want to factor it. And we'll still solve it graphically. And this problem is so exciting because it points out the danger of doing everything graphically without any analysis. So we have x squared minus 1x minus 12 over x squared plus x minus 6. And we know that we're going to factor because we're very careful mathematicians. And that'll be x minus 4x plus 3 and x plus 3, x minus 2. And we're saying, when is that greater than 0? So we're still going to solve it graphically. We'll type in all right. A very simple graph, indeed. The vertical asymptote is at 2. The horizontal asymptote is at 1. So we can go ahead and make a nice graph. The vertical asymptote is at 2. And the horizontal asymptote is at 1. And we had a swoopy down below and a swoopy above. Is that all correct so far? And so the question is, when is this above the x-axis? So when is it above?
From
Negative infinity up to 2, and then a little bit of a jump. So we get to here, and then we keep going. So first of all, where's that point? That point is at 4. So again, from 4 to infinity. So we're looking at these, that big swoopy here, and again from here up there. So in terms of an interval or a number line, we're going 2, 4. We're going from negative infinity, negative 2, and then from 4 up to infinity. But are either of those closed circles? And because it's strictly greater than 0, we're not interested in where it touches the x-axis. So they are strictly open circles. And that's an asymptote, so that's also an open circle, because an asymptote never actually gets to x equals 2. Okay, so then is that the end of our answer? From negative infinity to negative 2, union from 4 to infinity? Does that look good?
I have a question.
Yeah.
Is a negative 3 not a vertical asymptote because it's a hole?
Right, so now, folks, let's go back now. We actually didn't finish. What can we do with the x plus 3? And it cancels, which means that's a hole, which means there's a hole at x equals negative 3, which means that at negative 3, there's a hole there. It's what? Yeah, and since there's a hole there, is there a value there? No. Wait a minute, that meant to be 2. Oh no, folks, that was supposed to be a 2, right? Not a negative 2. Very sorry. Okay, but now coming over this way, at negative 3, there's a hole.
So if you negative infinity to
right, so it's actually negative infinity to negative 3, and then union from negative 3 to 2, and then from 4 to infinity. And you'll notice that we would have never noticed that hole from the graph alone. It was only from doing an analysis of the equation itself which told us there was a hole, which means that the graph was not positive at negative 3, because there was no value at all at negative 3. So that was a real good problem, because you had to look at it from both ways. Okay, we're going to take a 10-minute break. Oh, yeah. Okay, well, that's wonderful. We got through a good chunk of material today. What questions would you like to ask before we go? I know I need to go back in to the system and make sure that there are actual problems to do for 4.0. And I already changed the due date, so it is midnight. And I'll even give you all another couple days on it, because if some of you didn't see the problem, and we only just today did it in class, that's only fair that I